Okay, in the second part of 4.4, we're going to take the theorem that we learned previously, the if two points are equidistant, then they form the perpendicular bisector, and we're going to use that in the reverse way. So we're going to switch up the if and the then. So let's take a look at what we've got here. It says trace over line X in green, so I'm going to do that, and you can use any color you have. And it says if line X, that's this guy right here, is perpendicular bisector of the segment PQ, what do you know about points A, B, C, and D? So think about it. If this is the perpendicular bisector, A to P and A to Q, doesn't this point have to be equidistant from P and Q? And then wouldn't that be the same if I looked at point B? Wouldn't the distance to P have to be the same as the distance to Q? And then if I looked at point C, the distance from C to P would have to be the same as the distance from C to Q. I could look at point D. The distance from D to Q is the distance from D to P. And I have one other point on there, so I could do the distance from E to Q is the distance from E to P. All right, so what we're trying to show here is that any point on the perpendicular bisector is equidistant from the endpoints of the segment. And this is really important that you know where the endpoints of the segment are. We were dealing with segment PQ. We have the perpendicular bisector of PQ. Therefore, any point on that perpendicular bisector is equidistant from P and Q. A to P and A to Q is the same. C to P, C to Q, etc. So that's the direction we're going to be using the theorem today. If you already have the perpendicular bisector, anything on it will be equidistant. All right, so let's write that up in the reverse manner here. So we are going to say if a line is, the perpendicular bisector of a segment, then all points on the perpendicular bisector will be equidistant from the endpoints of the segment. So in other words, if this line right here is the perpendicular bisector of that segment AB, then I could pick any point I wanted on it. So for example, I might pick some point C. I would know that C to A has to be the same as C to B. C is equidistant from A and B. What does that mean to be equidistant? It means the distances are equal. So that means if C is on that perpendicular bisector, that CA is congruent to CB. That's what equidistant means. It gives us a pair of distances that are equal. So we're going to look at just 3 examples today. In this first one, we're given that AD is the perpendicular bisector of EC. That's all we're given. I like to continue to mark it in green. So AD is my perpendicular bisector, and my segment is EC, which is this segment. So there's the segment. So I'm going to box in those points. So we're talking about being equidistant from C and E. All right. So using the theorem in this direction, if a line is the perpendicular bisector, that's what we have, then all points on it will be equidistant from the endpoints of the segment. Well, the only points I have labeled right here, can't see this here, are A and D. So these 2 points should be equidistant from C and E. So let's start with A. That means the distance from A to C should be the same as the distance from A to E. And then I could also do point D, and I know the distance from D to C should be the same as the distance from D to E. I'm going to say if perpendicular bisector, then all points equidistant. So I'm kind of reversing the order there. All right, so let's mark that. Let's see what we have here. I have AC congruent to AE, and I have DC congruent to DE. All right, now where do I go from here? Right? I actually probably need to label another point here because I'm realizing that this point doesn't have a label on it. I think I could have also added BC congruent to BE. So add a label there. For some reason that got left off. So all of these points, A, B, and D, they were all on the perpendicular bisector, so they are all equidistant from C and E. So let's label these two. All right, so now the question is, how am I going to get angle 1 and angle 2? Well, I want you to first look at this big triangle right here, and maybe even look at it sideways. This big triangle has these two sides congruent. So if those two sides are congruent, aren't these two angles congruent? So I can say angle ACD is congruent to angle AED. This is line 3. I'm having trouble counting. If sides, then angles. But now instead of looking at this big triangle, can you cover this part up and just look at this triangle right here? Right? In this small triangle right here, if you look sideways, don't I have these two sides congruent? So if those two sides are congruent, looking at this triangle, can't I get these two angles congruent? Or maybe I should mark them this way to make it different. So that would be angle, what, BCD congruent to angle BED by the same reason. If sides, then angles. Now hopefully you see it. We have overlap and we have overlap. So in step 4, we can get angle 1 congruent to angle 2 by if congruent angles are subtracted from congruent angles, then the differences are congruent. Okay. All right, we're going to actually skip the second example because I don't think we need a full 4 examples today, and I like these next 2 better. All right, so let's take a look at this one right here. We are given a lot of information. We are given MN is the perpendicular bisector of JK. All right, let's mark that. MN is the perpendicular bisector, so I'm going to mark that in green. And it's the perpendicular bisector of the segment JK. So I'm going to darken that, and I'm going to box in J and K. That means all points on it are equidistant from J and K. All right, let's stop right there for a minute before I even write the rest of the given, because I'm looking at this green line and the only points I have marked are M and N. So if M is equidistant, doesn't that mean MJ is congruent to MK? Okay, and the only other point I see on there is N, so I could say NK is congruent to NJ. And that's by my new theorem. If we have a perpendicular bisector, then all points on it are equidistant. And of course, they're equidistant from these endpoints of the segment that's in question. All right, so use that piece of given. I have a lot of midpoints. So to shorten this up in the given, I'm just going to say A, B, C, and D are midpoints. Instead of writing all the segments, I think we can see what they're midpoints of. When I have multiple midpoints, I hope you're remembering from a couple chapters back, when I have midpoints, midpoint, midpoint, probably want to think about multiplication or division, right? To multiply, we'd go from littles to bigs. To divide, we'd go from bigs to little. So look at these midpoints. I'm looking at this segment that has a midpoint. I have the big. Isn't there a matching big over here? So I have 2 big segments congruent with 2 midpoints. So if the bigs are congruent, can't I divide to get the littles? I think the littles I want are AJ and BK. I hope you can see we're probably going after some triangles here. AJ congruent to BK. That would be if segments congruent, then like divisions are congruent. I had bigs that matched and 2 midpoints. Now down here I have another set of bigs that match. Notice this one matches this one, but I also have midpoints on those segments. So if I have bigs, I can once again divide to get littles. I need to be marking these differently, sorry. I think I'm going to take that little and that little. So that would leave me JC congruent to DK by the same exact reason. I had two big segments congruent with midpoints, so if these big ones are congruent, their halves are congruent. Now I hope you're starting to look here at these triangles, and I'm in pretty good shape. I have 2 points. Hopefully you've noticed that the segments we need are corresponding parts. Well, how the heck am I going to get another part? Because it doesn't look like I have anything else in the given. So I'll give you a hint, right? How about you just look at the top half of this picture? And if you look at the top half of the picture and you see that these two segments are congruent, think back to the last chapter, right? This triangle is isosceles. So if these two sides are congruent, aren't these angles congruent? And then if I flip that around and you kind of look at this upside down, isn't this triangle also isosceles because I have these two sides congruent? So if sides, then angles gets me those two congruent. Think about how those are going to help us as we write them. That's angle, if I do the top two, that's angle AJK congruent to angle BKJ. And the ones on the bottom, I could say CJK congruent to DKJ. Right? And that was by if sides, then angles. That's a really easy theorem to use, but we often don't recognize it in diagrams. So look for those isosceles triangles. That gives you both sides and angles. All right, now what can I do here? I have congruent angles right next to each other. I'm looking at these shaded triangles. I think I want to add them. So that gets me angle AJC congruent to angle BKD. If congruent angles added to congruent angles, then the sums are congruent, which gets me this whole one congruent to this whole one. And then I think my triangles are congruent. I hope you see that by side angle side. And then by corresponding parts, this is all old stuff, I get A, C, and BD. If triangles are congruent, then corresponding parts are congruent. A little off the screen there, sorry. Okay, and one last one that's actually pretty short, but I really like it, and you'll see why in a minute. I won't give away all the fun. We have AB congruent to BC. Let's mark that. AB is congruent to AC. Well, if I'm thinking of this in terms of equidistance, I'm going to stop right there for a moment. It appears to me that point B is equidistant from A and C. Right? I hope you can agree. The distance from B to A and B to C are the same. So I kind of want to box these in thinking B is equidistant from those 2 points. Look at the rest of the given. AE congruent to EC. Let's mark that. Doesn't that give us another point? Point E, that's equidistant from A and C. So you should remember from the last video, if I have 2 points that are equidistant, together they form the perpendicular bisector of, AC, which isn't even in my diagram. So that's how I know initially to draw AC. I'll draw that in there. And now this given, I have B equidistant, I have E equidistant, so now I can say BE, which forms a line, it doesn't just have to be the segment, it can be this whole line BE, is the perpendicular bisector of AC. That's what we learned in the previous video. If 2 points are equidistant from the endpoints of a segment, then they form the perpendicular bisector. So we're abbreviating. Well, that's not what we wanted to prove. We need AD congruent to DC. Well, now we're going to go the other way. Now I know I have a perpendicular bisector. So you know how in the previous problems we were making it green? Now I know I have this. Now I know BE is the perpendicular bisector of AC. Now, can't I use the theorem in the opposite direction? If a point is on the perpendicular bisector, it's equidistant, because B and E aren't the only points on that line. If you look at collinearity, these points are all together on a line. So D is also on the perpendicular bisector. So now I can say DA, the distance from D to A, is congruent to DC. Using this in the reverse direction, I can say if I have a perpendicular bisector, which I established in step 3, then all points on it are equidistant, and point D happens to be another point on that green perpendicular bisector. So again, I really like this one a lot because it really forces you to use the theorem in both directions. Here I'm using it the way we first learned it, and now once I established a perpendicular bisector, I can use any other point on it to get equidistance.